Hello and welcome to my YouTube channel ChemWis. In this video, we are going to discuss a very important topic, that is the application of Huckel Molecular Orbital Theory for 1,3-butadiene. We will discuss the following points: Huckel Molecular Orbital or pi molecular orbital, secular determinant, Huckel Molecular Orbital energy levels, the pi bond energy and delocalization energy, the coefficients and the Huckel molecular orbital functions, and lastly we will discuss physical representations of Huckel molecular orbitals, where we will discuss both the graphical and three-dimensional representations. Let's take one by one. This is 1,3-butadiene. There are 4 pi electrons delocalized across 4 carbon atoms C1, C2, C3 and C4. The general expression for the Huckel molecular orbitals or pi molecular orbitals can be written like as: psi is equal to A1 phi 1 plus A2 phi 2 plus A3 phi 3 plus A4 phi 4, where psi is the Huckel molecular orbital, phi 1, phi 2, phi 3 and phi 4 are pz atomic orbitals of C1, C2, C3 and C4 involved in pi bond formation, and A1, A2, A3 and A4 are orbital coefficients. Secular determinant. Formation of secular determinant is a very important step, since in 1,3-butadiene there are 4 carbon atoms across which pi electrons are delocalized, so there will be determinant of 4 into 4 matrix. For making determinant, keep 3 points in mind. Every carbon atom is attached to itself. For that, put X. For a carbon attached to another, put 1. And for a carbon not attached to another, put 0. Now let's make determinant. For that, first consider C1. Since C1 is attached to itself, so put X here, and C1 is attached to C2, so put 1 here. C1 is not attached to C3, so put 0 here. C1 is not attached to C4, so put 0. Now consider C2. Since C2 is attached to C1, so put 1 here. C2 is attached to itself, so put X here. C2 is also attached to C3, so put 1 here. C2 is not attached to C4, so put 0 here. If we consider C3, C3 is not attached to C1, so put 0 here. C3 is attached to C2, so put 1 here. C3 is attached to itself, so put X here. And C3 is also attached to C4, so put 1 here. If we consider C4, since C4 is not attached to C1, so put 0 here. C4 is not attached to C2, so put 0 here. C4 is attached to C3, so put 1 here. And C4 is attached to itself, so put X here. This will be equal to 0, where X is equal to alpha minus E upon beta. Alpha is the energy of an electron in a 2p orbital. Beta the interaction energy between two 2p orbitals, which is always negative, and E is the energy of a particular Huckel molecular orbital. This is a determinant of 4 into 4 matrix. Before solving it, we should know that the sign varies alternatively as plus, minus, plus and minus. Now let's break it into smaller matrices. For that, first write X and then multiply it with 3 into 3 matrix, which can be formed by ignoring figures in front of X. So the 3 into 3 matrix will be X10, 1x1, 0, 1x. The second place is negative and there is 1. So put minus 1 here and multiply it with a 3 into 3 matrix formed by ignoring figures in front of 1. So it will be 1, 1, 0, 0x1, 0, 1x. The third place is positive and there is 0. So put plus 0 and multiply it with 3 into 3 matrix formed by ignoring figures in front of 0, which is 1x0, 0, 1, 1, 0, 0x. The fourth place is again negative and there is 0. So put minus 0 and multiply it with 3 into 3 matrix formed by ignoring figures in front of 0, which is 1x1, 0, 1x, 0, 0, 1. The value of these two segments will be 0 as the coefficients for the matrices are 0. So there is no need to solve these two matrices. Now we will break the first two 3 into 3 matrices. These are plus, minus, plus, plus, minus, plus. Now break the first matrix. X multiplied by X multiplied by 2 into 2 matrix formed by ignoring figures in front of X, which will be X1, 1X. The second place is negative and there is 1. So write minus 1 and multiply it with 2 into 2 matrix formed by ignoring figures in front of 1. So it will be 1, 1, 0x. Third position is positive and there is 0. So write plus 0 and multiply it with 2 into 2 matrix formed by ignoring figures in front of 0, which will be 1x, 0, 1. Now write minus 1 and break the second matrix. It will be 1 multiplied by 2 into 2 matrix formed by ignoring figure in front of 1, which will be x1, 1x. Minus 1 multiplied by matrix 2 into 2 matrix that will be formed by ignoring figures in front of 1, that will be 0, 1, 0x, plus 0 multiplied by 2 into 2 matrix formed by ignoring figures in front of 0, that will be 0x, 0, 1. These all will be equal to 0. Ignore these terms as they are equal to 0. Further simplification by solving 2 into 2 matrices will give x into x square minus 1 into x minus 0 plus 0 minus 1 into x square minus 1 minus 0 plus 0 is equal to 0, or x into x power 3 minus x minus x minus x square plus 1 is equal to 0, or x power 4 minus 3x square plus 1 is equal to 0. Now let's solve this equation. For that, suppose x square is equal to y. So the equation will become y square minus 3y plus 1 is equal to 0. Let's compare it with a general quadratic equation, ax square plus bx plus c is equal to 0. The solution for the general quadratic equation is x is equal to minus b plus minus under root b square minus 4ac upon 2a. In the given equation, a is equal to 1, b is equal to minus 3 and c is equal to 1. So we can write y is equal to 3 plus minus under root 3 square minus 4 into 1 upon 2 into 1, or y is equal to 3 plus minus under root 9 minus 4 upon 2, or y is equal to 3 plus minus under root 5 upon 2. If we multiply numerator and denominator by 2, then the equation will become y is equal to 6 plus minus 2 root 5 upon 4, or we can write y is equal to 1 plus 5 plus minus 2 root 5 upon 4. We know that a square plus b square plus minus 2ab is equal to a plus minus b square. So we can write y is equal to 1 plus minus 2 root 5 upon 2 square. So there will be two values of y. y1 is equal to 1 plus 2 root 5 upon 2 square, and y2 is equal to 1 minus 2 root 5 upon 2 square. Since we have supposed that x square is equal to y, so x is equal to plus minus under root y. So there will be four values of x. x1 is equal to plus 1 plus 2 root 5 upon 2 is equal to 1.618. x2 is equal to minus 1 plus 2 root 5 upon 2 is equal to minus 1.618. x3 is equal to plus 1 minus 2 root 5 upon 2 is equal to minus 0.618, and x4 is equal to minus 1 minus 2 root 5 upon 2 is equal to plus 0.618. Huckel molecular orbital energy levels. We know that x is equal to alpha minus E upon beta. This equation can be rearranged as E is equal to alpha minus x beta. Since there are four values of x, minus 1.618, minus 0.618, plus 0.618 and plus 1.618. So there will be four Huckel molecular orbital energy levels. Putting x is equal to minus 1.618 will give E1 is equal to alpha plus 1.618 beta. Putting x is equal to minus 0.618 will give E2 is equal to alpha plus 0.618 beta. Putting x is equal to plus 0.618 will give E3 is equal to alpha minus 0.618 beta, and putting x is equal to plus 1.618 will give E4 is equal to alpha minus 0.618 beta. Since beta is a negative value, so E1 is less than E2, E2 is less than E3, which in turn is less than E4. E1 and E2 are bonding Huckel molecular orbital energy levels. while E3 and E4 are antibonding. Thus, we can draw the Huckel molecular orbital energy levels for 1,3-butadiene system like this. These are E1, E2, E3 and E4. In 1,3-butadiene, there are 4 pi electrons. So, in ground state, 2 will stay in E1 and 2 in E2. The pi bond energy and delocalization energy. Before bonding, all the 4 pi electrons will stay in alpha. So, the total energy of 4 electrons before pi bonding is equal to 4 alpha. Total energy of 4 electrons after pi bonding is equal to 2 into alpha plus 1.618 beta plus 2 into alpha plus 0.618 beta is equal to 4 alpha plus 4.472 beta. Pi bond energy, which is energy of 4 electrons after pi bond formation minus energy of 4 electrons before pi bond formation, is equal to 4 alpha plus 4.472 beta minus 4 alpha is equal to 4.472 beta. If there is no delocalization, the 1,3-butadiene system will be like 2 ethylene units, and the pi bond energy without delocalization will be 2 into 2 beta is equal to 4 beta. So delocalization energy is equal to pi bond energy when there is delocalization, that is 4.472 beta, minus pi bond energy when there is no delocalization, that is 4 beta, is equal to 0.472 beta, which is a negative value, as beta is a negative value. The negative value of delocalization energy suggests that the delocalization decreases the energy of 1,3-butadiene system and thus increases stability. The coefficients and the Huckel molecular orbital functions. Let's rewrite the secular determinant we created for 1,3-butadiene system. Since the 4 coefficients are A1, A2, A3 and A4, so we can write A1, A2, A3, A4 multiplied by 4 into 4 matrix is equal to 0. So we can write the 4 secular equations. A1x plus A2 is equal to 0. A1 plus A2x plus A3 is equal to 0. A2 plus A3x plus A4 is equal to 0. And A3 plus A4x is equal to 0. For bonding level E1, x is equal to minus 1.618. Putting x is equal to minus 1.618 in the first secular equation gives A2 is equal to 1.618 A1. Putting x is equal to minus 1.618 and A2 is equal to 1.618 A1 in the second secular equation gives A1 plus 1.618 A1 into minus 1.618 plus A3 is equal to 0, or minus 1.618 A1 plus A3 is equal to 0, or A3 is equal to 1.618 A1. From these two equations, A2 is equal to A3 is equal to 1.618 A1. Putting x is equal to minus 1.618 in fourth secular equation gives A3 is equal to 1.618 A4. From these two equations, A4 is equal to A1. Now applying normalization condition, which is A1 square plus A2 square plus A3 square plus A4 square is equal to 1. Putting the values of A2, A3 and A4 in terms of A1 in this equation will give A1 square plus 1.618 square A1 square plus 1.618 square A1 square plus A1 square is equal to 1, or A1 square plus 2.618 A1 square plus 2.618 A1 square plus A1 square is equal to 1, or 7.236 A1 square is equal to 1, or A1 is equal to 0.372. So A2 is equal to 1.618 into 0.372, or A2 is equal to 0.602. Since A3 is equal to A2, so A3 is equal to 0.602. Since A4 is equal to A1, so A4 is equal to 0.372. We know that the general expression for Huckel molecular orbital is psi is equal to A1 phi 1 plus A2 phi 2 plus A3 phi 3 plus A4 phi 4. Putting the values of A1, A2, A3 and A4 in this equation will give Huckel molecular orbital function for E1 as psi 1 is equal to 0.37251 plus 0.60252 plus 0.60253 plus 0.60254. For bonding level E2, X is equal to minus 0.618. You can perform similar calculations as we have just done for E1. It will give A1 is equal to 0.602, A2 is equal to 0.372, A3 is equal to minus 0.372 and A4 is equal to minus 0.602. So the psi 2 will be equal to 0.60251 plus 0.37252 minus 0.37253 minus 0.60254. For anti-bonding level E3, X is equal to plus 0.618. So A1 will be equal to 0.602, A2 is equal to minus 0.372, A3 is equal to minus 0.372 and A4 is equal to 0.602. So psi 3 will be equal to 0.60251 minus 0.37252 minus 0.37253 plus 0.60254. For anti-bonding level E4, X is equal to plus 1.618. So A1 will be equal to 0.372, A2 is equal to minus 0.602, A3 is equal to plus 0.602 and A4 is equal to minus 0.372. So A4 will be equal to, so psi 4 will be equal to 0.37251 minus 0.60252 plus 0.60253 minus 0.37254. Physical representation of Huckel molecular orbital functions. Let's rewrite the wave functions psi 1, psi 2, psi 3 and psi 4 for the four Huckel molecular orbitals of 1,3-butadiene system. There are two methods for their physical representation, graphical and three-dimensional. Let's first discuss graphical representation. These are the graphs obtained by plotting psi with respect to the distance as we move along axis containing C1, C2, C3 and C4 carbon atoms. Psi 1 can be represented like as: there are 4 peaks, all are in positive phase because all the four coefficients A1, A2, A3 and A4 are positive. The area under a peak is proportional to the magnitude of coefficient. There is no node or radial node in psi 1. If we see psi 2, peak 1 and peak 2 are in positive phase while 3 and 4 in negative phase, because in psi 2 A1 and A2 are positive while A3 and A4 are negative. This point on the axis having C1, C2, C3 and C4, where psi 2 is 0, is called node or radial node. Psi 3 is represented like as. In this, peak 1 and peak 4 are in positive phase while 2 and 3 are in negative phase. This is because A1 and A4 are positive while A2 and A3 are negative. In this, there are two radial nodes. In psi 4, phase changes alternatively. In this, there are three radial nodes. Now come to the three-dimensional representation. We know that Huckel molecular orbitals are formed by linear combination of pz atomic orbitals. If we first consider psi 1, we can show that 4 pz atomic orbitals involved in its formation like as, where the positive lobes of each pz atomic orbital is above the plane containing C1, C2, C3 and C4 atoms, while negative lobes of each below that plane. This is because all the coefficients, that is A1, A2, A3 and A4 are positive. Here, the size of lobes is directly proportional to the magnitude of the coefficient. So, all the 4 positive lobes will combine to make a single positive lobe, and all the 4 negative lobes will combine to make a single negative lobe, and thus the psi 1 will look like this. If we take psi 2, the 4 pz atomic orbitals can be represented like as lobes of the same sign in the same phase will combine together to produce 2 positive and 2 negative lobes, and the psi 2 will look like this. The 4 pz atomic orbitals of psi 3 can be represented like as. Here, the negative lobe of 2 and 3 will combine to make one negative lobe, and positive lobes of 2 and 3 will combine to make a positive lobe. Lobes of 1 and 4 will not combine. So, the psi 3 will look like this. These are the pz atomic orbitals of psi 4. Here we can see that none of the two adjacent pz atomic orbitals are in the same phase. So none will combine together and the psi 4 will look like this. If we talk about nodal planes, psi 1 has only one nodal plane which contains the axis having C1, C2, C3 and C4 carbon atoms. This is common to all. Psi 2 has one additional nodal plane perpendicular to the axis containing C1, C2, C3 and C4. Psi 3 has 2 additional nodal planes while psi 4 has 3. If you look at psi 1, there is no center of inversion, so it is called ungyred and also expressed by pi u. Psi2 has inversion center, so it is called G-rad and is represented by pi g. Psi3 having no inversion center is ungirad and is represented by pi u, and Psi4 with inversion center is G-rad and is represented by pi g. That's all in this video. Please subscribe my channel and press the bell icon if you like this video. Thank you very much for watching this video.